We were talking about the third example in the kinetic energy section, and I had finished it, and so I just want to return to it. In question number 3, we were calculating the speed of the ball, and the answer was 45.0 meters per second. Now, just to remind us, I showed you yesterday, but I'll show you again because we're going to do another problem in this area, that when you'd like to calculate the speed of the baseball, you have to manipulate the kinetic energy formula. Now, as a side note, I teach this class in French, and in French, the word kinetic starts with a C, not a K. If I ever write EC, I'm not trying to be tricky. I'm just forgetting which language I'm actually thinking in. Anyways, to manipulate this formula so that we can find the value of V, which is speed, we have to take everything that's on the same side of speed and move it to the other side. And to do that, we do the mathematical opposite. So I'm going to start by multiplying both sides by 2. That gets rid of my 1/2. I'll divide both sides by m. That gets rid of mass. And then I put a square root on both sides, because that is the opposite of the power of 2. So the result that we saw was that speed is the square root of 2 times kinetic energy divided by mass. And what I told you yesterday was, please, if your calculator doesn't already do it, put brackets so that that entire calculation happens first, and then you take the square root of it. So we'll do question 4, because it's similar to question 3, to give you one more example of how to find speed using the kinetic energy formula. I'm going to start right away with the formula already manipulated, since we just saw it. In this example, I have a mass, and my mass is already in kilograms. I have kinetic energy, which is in joules, which is what I want. So I don't have to change any of the units. I simply have to put them into the formula. So please try this on your calculator and make sure you are getting the same answer that I'm getting. What I find more often than not isn't that you don't know how to put numbers in a formula. It's that when you type things into your calculator, something goes wrong, and what you've written and what you're calculating aren't the same thing. You should be doing the square root of 2 times 18 divided by 7.4. If you type it into your calculator correctly, the result should be 2.2 meters per second. So what we'll see is that mechanical energy isn't a new, different kind of energy. It's actually the energy that we've already talked about combined together. Mechanical energy is due to the motion, so we're talking about kinetic energy, and the position, so we're talking about potential energy of an object. So far, our examples have only been an object that is moving or an object that is above the surface of the Earth, but never both. And so in the next set of examples, we'll talk about things that are doing both. This means that when we're calculating mechanical energy, what we're really doing is taking our potential energy, which is usually due to gravitational potential energy, which is why I wrote a G there. You might remember I mentioned way back in the beginning, sometimes we actually write a G to specify which type of potential energy. So mechanical energy is potential energy plus kinetic energy. So it's not actually a new formula. It's simply two formulas that you already know put together. That means that if I want to calculate mechanical energy, I'm just going to take the formula for potential energy and add it to the formula for kinetic energy. Now, the order of operations dictates that we always multiply before we add, which means that I recommend you put some brackets when you're doing this calculation. Especially when we're talking about mechanical energy, there will be lots of numbers. We're not doing something that's particularly difficult. We're just multiplying a bunch of things and then adding them together. But when you have a lot of numbers, it is easy to forget to type something in. So I'm just going to point out a couple of things that I find that people often forget when they're doing a mechanical energy calculation. Either in this formula or just the kinetic energy formula, I find that people frequently forget the 1/2 part, the part where it's a 0.5 or that you have to divide by 2. And so this is why it's important to write the work that you're doing, so that when you're typing things into your calculator, you can just look at your page and type all of the things that you've written as your work. You could also go back and check, once you've typed it in, that it looks the same way that you wrote it on your paper. The other thing that I find is that sometimes when we have something with a power, like here we have v squared, depending on your calculator, sometimes this messes things up. On a TI calculator, the fancy kind that a lot of you have, your calculator is really good at knowing when the square is supposed to be applied. But I find that on other types of calculators, maybe where it's calculating kind of as you go along, sometimes the square, the power of 2, gets applied to the whole formula. And so what I recommend to people to do is to put the v squared part inside of its own set of brackets, just to make sure that that power of 2 is only going with the v and not with any of the other numbers that you're using. Now that's a few particularities about the formula. Since we are talking about energy, it is measured in joules. All the types of energy are measured in joules. Potential, kinetic, or mechanical, joules is always the unit for energy. Since that's the case, just like in the other formulas, mass has to be in kilograms and height has to be in meters. So that's not different from the other energy formulas that we've used. Now the next point explains to you an idea about energy conservation. We'll talk a little bit later about something called the laws of thermodynamics, but in brief, the idea is that energy is always conserved. What that means is that I can't make energy disappear. If something had one type of energy, and all of a sudden it has less of that type of energy, it must have more of some other type. Now, since our focus is things that are moving, that's what our topic is here in Science 10, when we're talking about energy conservation, we'll be talking about potential energy of whatever form, chemical, elastic, or gravitational, getting converted to kinetic energy. Now, it could be other forms, but we're not going to focus on the other forms. We're going to focus on kinetic energy. And vice versa. That means the opposite is true. So we'll talk about a bunch of examples where an object had potential energy and then used that potential energy to have kinetic energy. Or perhaps an object had kinetic energy and that gave it some potential energy. The idea is that total energy, which is what mechanical energy refers to, always remains the same. So an idea that will often help you calculate things is the one that I've noted next. The potential energy at the top. and the top is really general here. But by the top, I mean the highest point in that particular object's movement. So it would be a different height for every situation, but whatever that object's highest point is, we'll call that the top. Whatever its potential energy is there should equal the kinetic energy at the bottom, and here bottom means right as we're getting towards the surface of the Earth, because that's how we calculate potential energy. So what I've written here isn't necessarily a formula, it's an idea. It's something that you can use because you know the formula for potential and kinetic energy to help you calculate answers. The idea is that EP at the top is equal to EK at the bottom. And so I've got a couple of little pictures here to help illustrate to you what I mean by this. Both of my examples are with a roller coaster. So on the right, we have a very simple little roller coaster track. Over here, we'll call this the top. So when the roller coaster is at the top of its track, the highest point, which in a roller coaster that functions properly should be the very first hill that it climbs. When the roller coaster is at the top and it hasn't started moving yet, it's just kind of paused there waiting to fall, we would have high, or sometimes I use the word maximum, potential energy, and low or minimum kinetic energy. For the purposes of our calculations, we'll assume that that means 0. So right before the roller coaster starts to fall down that first hill, we'll assume that it's not moving, even if it's for a brief second before it starts to go down. Kinetic energy at the top will be 0. What this means is that since none of its energy is kinetic, all of its energy is potential, its potential energy and its mechanical energy will be the same number. Since mechanical is the total, and we just said kinetic energy will be 0, that means that all of its energy is potential. Now the same will be true at the bottom. At the bottom, you have minimum potential energy, so we'll say 0, and you have maximum kinetic energy, and your kinetic energy will be equal to your mechanical energy. So what we're trying to illustrate is that the total amount is always going to be the same. Mechanical energy shouldn't change as an object is moving. The amount of it that's potential and the amount of it that's kinetic, the proportion will change, but the total will always be the same number. That means that at a spot like this one, which is neither the highest nor the lowest spot, is a spot where we would actually have to add them together. So at that particular spot, potential energy wouldn't be 0 because we're above the surface, and kinetic energy wouldn't be 0 either because it's still moving. So if I was to give a pretend imaginary number to all this, if my mechanical energy was 100 joules, it would be 100 joules here, 100 joules here, and 100 joules there. It would be the same value everywhere. Now what would change is how much each type, potential and kinetic, was actually contributing to it. At the top, my potential energy would be 100 joules. All of my mechanical energy would be coming from potential energy. At the bottom, my kinetic energy would be 100 joules. And in the spot that's slightly above the surface, since it's not very high, we'll assume that kinetic is contributing a bit more than potential. I'm just doing an estimation here. I'll show you later how to calculate this. But we'll say at this spot that 75 joules are kinetic energy and 25 joules are potential. The total is always 100. It's just how much I have of each type that is changing. So something I would ask you to do on a test as like a written question would be not to calculate something like this, but to explain, like with words or with a picture, what's happening. The picture on the left here, I had just so I had another picture of a roller coaster because I wanted to show you one more idea. On this picture, you very clearly see that first slope of the roller coaster path. And the idea would be that for the roller coaster to get to the top, some sort of gear mechanism pulls it up. And so what I want to mention is that that would be work. If that roller coaster is being pulled or pushed up the track with a force, that is work. That work could then be equal to the mechanical energy that the object has. And I'm mentioning this because our goal is to show you that work done gives energy to the object on which the work was done. If you know that, you can calculate work and use that value to find other things like the mass or the speed of the object. Would anyone like to ask any questions about this description, this explanation here? So in this first section, we're focused on mechanical energy of an object that is neither at its highest nor its lowest point. So in all of these examples, we are basing them on this idea. Mechanical energy is the sum of potential and kinetic energy. In the first example, I can see a speed. Now, it's fairly important that the speed is horizontal because kinetic energy doesn't involve a height, and you guys don't yet know the way to calculate the vector that this would be. I won't ask you a question where this is not the case, but just so in case you were wondering, that's why the word horizontal is there. I have a mass. So there's a bird flying with a clam in its mouth. That's the mass of the clam. I know mass needs to be in kilograms, so I'm going to switch that right away so that I'm using the correct value in my calculation. The question is asking me to calculate total mechanical energy, so EM, and it tells me a distance above the ground. That tells me that this is height, or distance, but probably height. It also tells me, since I'm above the ground, that I might want to use the value for gravity. Now, I can't emphasize enough that when we get to the end of this unit, and we're doing the unit test, it's really important that you decide what formula you're going to use. I heard someone say earlier today, we're just putting numbers in formulas. That's not that hard. And I agree. It's not once you know which formula you're going to use. So always make sure that you identify the variables that you have so you can make a good decision. Now, in this case, I know I want mechanical energy, which means I'm going to add together potential and kinetic energy. That means I can take their two formulas and add them together. So that means I can do mgh plus 1/2 mv squared. And the values that I'll put in each of those spots would be 0.3 kilograms. times 9.81 meters per second squared times 30 meters plus 1/2 or 0.5, however you want to represent it, times 0.3 kilograms times 8 meters per second to the power of 2. Now, when you type this into your calculator, here is what I suggest. I suggest that you put brackets here. I also suggest that you put them here and there. In some of your calculators, this might end up being redundant. Your calculator might be smart enough to know the difference. But I want you to recognize that that power of 2 only applies to the 8. You could even square that number first before typing this into your calculator. Since this is a whole number, if this was me typing it into my calculator, I would just type 64, because I know that 8 times 8 is 64. That way, I wouldn't have to worry that that power of 2 was being attached to any other number that I was typing in. Now, if you type this into your calculator all properly, the answer that you end up getting should be 97.9 joules. So I'm going to pause here. All right, we're going to do the next example together, and then I'm going to ask you to do the third one, because the third one is very similar to the second one. In the second one, we start out with a 55-kilogram high jump athlete. That's the mass. They're leaping in the air to attempt to clear the bar. At the top of the leap, here's their total mechanical energy. And they're also moving. So in this particular scenario, the top of the person's path isn't where their kinetic energy is 0 because they're still moving. So we have a speed. We would like to know the gravitational potential energy of the athlete. Since I know that I can add potential and kinetic energy together to get mechanical, that tells me if I take mechanical energy and subtract kinetic energy, that will tell me how much potential energy I have. Now, maybe because this is the lesson we're doing today, this would be obvious to you right now. But I'll tell you what will happen. You will get to the test. You will say to yourself, that's potential energy. I can't answer the question. There's not enough information. It doesn't tell me how high the bar is. And you're right. It doesn't. And so what I'm reminding you of is, if you identify what variables you know, then you can decide which formula makes the most sense. I can't calculate gravitational potential energy this way. I don't know the height of the bar. I do know, for example, all of the pieces of the kinetic energy formula. And so on the left, I could do that subtraction and find the answer to potential energy. This idea that there's more than one way to calculate something is one that repeats itself often in physics. Other things that we've seen before would be something like velocity. Velocity you can calculate with distance and time, but you could also calculate velocity if you knew acceleration and time. It shows up in 2 formulas. So just be careful that you're not trying to force a formula where you don't know all of the information. I won't give you a question that you can't answer. And so there will always be a way to answer it. You don't have to force numbers into a spot they don't belong in. So in this particular calculation, here are the numbers that we'll use. 3.00 times 10 to the power of 3 joules minus, and then I'll put brackets so that I'm sure that my whole kinetic energy calculation happens before the subtraction. So I'll do 1/2 or 0.5, however you prefer to type it in, times the mass, which was 55 kilograms, times the speed, which is 8.33 meters per second, and that's to the power of 2. Now in this case, I don't off the top of my head know what 8.33 times 8.33 is, so I would likely type it in with brackets in my calculator. So give this one a try. Put those numbers in your calculator. If you are successful, the answer that you will get before you round it is 1091.8, which I would round off to 1.09 times 10 to the power of 3 joules. Okay, so just to make sure that we're all on the same page, the third example solution is up on the screen so that you can see. We're following the same sort of idea that we did for number 2. I know the total mechanical energy, and I want to know kinetic energy. Since mechanical energy is both of those put together, if I subtract potential energy from mechanical energy, that should give me kinetic energy. So I took my total mechanical energy and subtracted potential energy, mass times the acceleration due to gravity times height. In other words, 2 kilograms, 9.81 meters per second squared, times 50 meters. That is how I arrived at the answer 899 joules. Now before I show you some other types of examples, would anyone like to ask any questions about this? Where basically we're adding up potential and kinetic energy to make total mechanical energy. All right, so on your sheet of practice problems, there's a couple more sections. We're still talking about mechanical energy, but I'm going to show you some different types of calculations that you can do that are about mechanical energy. Is there anyone who's still writing this that needs this up? All right, so the next two examples, the first of which I will demonstrate for you, and the second of them you'll try yourself, illustrate to you the idea that potential energy at the top of an object's path and kinetic energy at the bottom of an object's path should be the same value. So in the first question, here's what we know. We know a mass. I have a mass of my water balloon. I know the height, 12 meters, and I would like to know speed. And I look at this and I say, well, geez, what formula do I know that has all of these things in it? And the answer is, it's not just one formula. I know that to calculate speed, I could use the kinetic energy formula manipulated for V like we saw earlier in today's lesson. And so I ask myself, do I know those things? Well, I definitely know mass. It tells me right in the question. Do I know kinetic energy? Not yet, but I will. For me to figure out kinetic energy, I'm going to remind myself that the kinetic energy that this object has right before it hits the ground will be the same as the potential energy it had at the top. So I ask myself, could I calculate potential energy? I know mass, I always know gravity because it's a constant, and I know height. I have enough information to calculate potential energy at the top. I know that potential energy at the top and kinetic energy at the bottom should be equal because of conservation of energy. So notice I'm not actually using mechanical energy as part of my calculation. I'm using the concept. I'm using the idea that energy is conserved. So in this question, you'll actually have two steps. The first thing that you'll do is calculate potential energy. That was great. So I will do mass, 10 kilograms, times the acceleration due to gravity, 9.81 meters per second squared, times the height, 12 meters. That's going to tell me potential energy. So the number that you get for this step is 1,177.2 joules. Now notice I'm not rounding off the answer there, and that's because this is not my final answer. I'm still going to do some more calculating. And if that's ever the case, earlier someone showed me that their answer for one of the questions was a little bit off, and we realized they had rounded a value that they calculated before they were done the whole question. So never round things off until you're at the very end of the question. Sometimes it won't change your answer that much. You might end up getting the right answer anyways. But other times it will change your answer enough that even when you round your answer off at the end, you'll have the wrong number. Now I take this value and use it as the value of kinetic energy. Now I know everything in that formula. I know mass, I already used it in the question. Now I know kinetic energy, and those are the only two things I needed to know to calculate speed. So my calculation for speed will look like this. Speed is the square root of 2 times 1,177.2 joules divided by 10 kilograms. The answer that I'll get is 15 meters per second. Now that is one very valid way of solving this problem. What I'd like to do is next show you an alternate method that you can use where you do the calculation in one step. Either way is fine. If you prefer this way, use this way. If you like the second way I'm going to show you better, use that way. They will both represent the same thing. Question? It is 15.3, not 15.0. Does anyone else have any questions that they'd like to ask here? So then I'm going to show you this other way. I'll do it down here so that I can leave this up on the screen. So I'm still talking about question number 1. Instead of doing 2 separate steps, I could do this calculation all in one step. I'm saying that potential energy at the top and kinetic energy at the bottom are the same. So I could start this question by taking those 2 formulas and making them equal to each other. I could say mgh equals 1/2 mv squared. I know all of the missing variables in this equation, so I just need to solve for v, and I'll show you how I would do that. Since m is on both sides, I can just get rid of it. What I'm actually doing is dividing both sides by m. So I don't even actually need to know the mass of the object to answer this question. It's there, but I'm not going to use it. I also need to get rid of this 1/2. So my solution is to multiply both sides by 2. I need to get rid of the power of 2. So I do a square root. The result is that speed is the square root of 2 times g times h. So notice, I'm not going to use the mass anywhere in the calculation. I could if I wanted to do the 2-step version, but if I'd like to do the 1-step version, I don't even need the mass. When I do this calculation, the square root of 2 times 9.81 times 12 you'll see that I get 15.3 meters per second, the exact same answer. Now, it doesn't matter to me which method that you choose. I will tell you, though, that at least once I'm going to make you have to use that version because I will not tell you the mass. And the only way that you could solve it is by making those two formulas equal to each other right away. Now, would anyone like to ask any questions about the first example? So the second example is based on the same principle. The mechanical energy is the same throughout. That means potential energy at the top and kinetic energy at the bottom are equal. In this question, you have a 30-kilogram child who's jumping on a trampoline. Here's their speed. And we would like to know how high the child will rise. So you can choose to answer this question one of two ways. You can do it in 2 steps, like I did the first question in 2 steps. Calculate the type of energy that you have enough information for. You know M and you know V. Which formula has M and V in it? It's the kinetic energy formula. So that's the one that you could start with first. Or you could follow my second example and say that the 2 formulas are equal right away, and you'd simply have to manipulate that for height. I will show you both ways after the fact. But I'm going to pause here so everyone can have a chance to try it.